Hello guys, hope you are all doing well. In this video I'm going to explain how to find prime numbers from 1 to n. In this type of question we will be given a number n and we have to print or return all the prime numbers in that range including n. So here I'm going to explain both the approaches, that is naive approach and efficient approach to solve this question. So starting with naive approach, let's dive in. So first of all I want to discuss how we'll find that a given number is prime or not. Suppose there is a number n, how we'll find that this is prime number or not. So we know that we will divide it from number 2 to n minus 1. We will one by one divide it from each number in this range, and if it gets divided then we will say that it is not a prime number, and if it don't get divided then we will say that yes, it is a prime number. Obviously we will not divide it with 1 and n, as every number is divisible, completely divisible by 1 and itself. So for our question in which we have to tell all the prime numbers, in that question suppose we have given an n 100 and we have to tell all the prime numbers from 1 to 100. So I will apply a loop that will start from 2 to n. So this loop is going to give me each number from 2 to n, here 100, one by one, and inside it I'm going to check if that number is prime or not. So I think you have noticed here that I have not started from 1, as 1 is not a prime number. 2 is the smallest prime number. So inside this, for checking that the number that is given by upper loop, let's say this here loop variable is I, so I will here run this loop from 2 to I minus 1, and inside this loop I'm going to check, let's say here loop variable is j, I'm going to check if I is completely divisible by j. It means that its modulo is 0, then it is not a prime number. So I will use here a flag variable of bool type. Initially it will be true, and if it get divided by the number, any number between 2 to n minus 1, I will update this flag with false. And inside this inner loop I'm going to check if flag is false and true. If it is true, then I will print that number, otherwise I'm not going to print that number. So this is the approach to find the prime numbers. So let's check its time complexity. See, this loop is running approximately n times, and this loop is also running n times. So overall time complexity of two nested loop and both running n times, its time complexity is going to be order of n square. So can we optimize it? Yes, we can optimize it. So let's see how. So we will use here a concept of divisor pair property. So what is that? So consider an example 12. Now how many divisor does 12 have? So it is 1, 2, 3, 4, 6, 12. So here we can observe that the divisors are forming pair like this: 12 and 1, 2 and 6, 3 and 4. When we multiply both the numbers of these pair, we get the original number. So 1 multiplied by 12 is 12, 2 multiplied by 6 is 12, 3 multiplied by 4 is 12. Now there is a division here. So it is square root of 12. So square root of 12 will be greater than 3 and less than 4, somewhere between 3 and 4. So this property tells that the divisors of any number forms pair, and if there exists a pair such that it is less than square root of number, then there must exist its counterpart in the next part. So there can be a special case for perfect square number such as 25, 16. So the both the pairs will be lie on this square root of number. So ignoring this special case, we will consider here, we will use this property to reduce the time complexity to improve our previous approach. How can we do that? So previously the inner loop that was running from 2 to I minus 1. Now we know that if we can check here in this part, if there is no divisor, then surely there will be no divisor in other part also. So we will check from 2 to square root of n, and when we can surely say that if we don't find any divisor in the first part, there will be no divisor in the second part. So we need to check only this part only. So this is the improvement of our previous approach. Now we'll see and another approach that is efficient than both these approaches. Now we'll discuss the best approach for this problem. It is known as sieve of Eratosthenes. So the main concept of this algorithm is that if there is a prime number, let's say 5 and its multiple 10, 15, 20, 25. Now here if I ask you a question that if accept the first multiple of the prime number, can any other its multiple be a prime number? Any of them can be a prime number? The answer is no, because all these numbers are product of two numbers. It is 5 into 3, it is 5 into 4, and it is 5 into 5. These are product of two numbers except one and itself. So multiples of a prime number cannot be a prime number for any prime number. So here I'm not going to check for each number that if it is prime or not. I'm going to mark all non-prime numbers. So at the end we will left with all the prime numbers that are not marked. So suppose the number given here is 50. So I will take array, bool type array of size n plus 1. Why plus 1 here? Because if I take only 50 here, so maximum index in the array can be 49. So I will not be able to mark this 50. So I have taken plus 1 so that I can have 50 as index. So this will be the indexes of my array. It will start from 0 till 50. So now in this I'm going to put a loop that will run from 2 to n, as 2 is the lowest prime number to n, and later we will see that we can even reduce this n. So initially I will mark these two numbers as non-prime numbers. Now inside this loop I am going to place another loop that is going to mark all the multiples of given prime that is given by upper loop. So I'm going to start with 2 as it is not marked and it is a prime number. So I'm going to mark all its multiples, that is 4, 6, 8, 10, 12, 14, 16, 18, 20 and 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48 and 50. Now I have marked all the multiples of 2 till the range given. Now I will move to the next number, that is 3. It is also not marked, so it is a prime number. So now I'm going to mark all of its multiples. So this loop will give, first it will give 2, then it will give 3, and this loop will mark the multiple of 3 this time. So multiple of 3 are, so there is an observation. So I'm going to write here the prime number which is able to mark its first multiple. So 2 is able to mark its first multiple, that is 4. Now we'll check for it for 3. So 3's multiple is 6. Is it able to mark it? No, it is already marked. So the first multiple, that is 9. So 3 is able to mark 9 as its first multiple. So I will write here. So this will be used to for making another observation. So I will write it 9 here. So now I will mark all the multiples of 3. So I have marked 9, 12 already marked. I will mark 15, 18 already marked. Then 24 marked, 27, 30 marked, 33, 36 marked, 39. Then 42 marked, then 45, then 48 marked. Then we'll move on to next number. So next number is 4. It is marked as non-prime. So we'll move ahead and we'll mark all the multiples of 5. As 5 is prime number, it is not marked. So let's see the first number that we'll able to mark with 5. So its second multiple is 10, already marked. Next multiple is 15, already marked. And next multiple is 20, already marked. So 25. So 25 is the first multiple that we are able to mark with 5. So I will write here separately with 5 I am able to mark 25. So now I'll mark next its next multiples. So 30 already marked, I will mark 35 here. 40 already marked. So then 45, then 50. So now I have marked all the multiples of 5 in the given range. So now I will move to the next number, that is 6. It is a non-prime number as it is already marked. So I will move to the next number, 7. Yes, 7 is a prime number. So I'm going to mark all its multiple. So I will write here 7. Now the first multiple that I am able to mark with 7 is, so it is not 14, already marked. It is not, so I think I have left here. So 21 must be marked while I am marking the multiples of 3. So it is not the first multiple that I am going to mark with 7. So 21 already marked, then 28 already marked, then 35 already marked, then 42 already marked. So 45 is the first number that I am able to mark with prime number 7. So I will write here 49. Now let's see for the next prime number, that is 11. 8, 9, 10 are not prime numbers as they are already marked. So I will write here 11. Now we'll see its multiple. So the first multiple I am able to mark with 11 is, so it is it 22? No, it is already marked. It is 33? No, it is already marked. Is it 44? No, it is already marked. And 55 is beyond range. So I am not able to mark anything with 11. Now 12 is a non-prime number, so I will not check. I will not mark for multiples of 12. Now I will take 13 as 13 is a prime number. Now I will try to mark its multiples. So its multiples are 26 already marked, 39 already marked, and then 51 beyond range. So I am not able to mark with 13 as well. So do you think we need to check, we need to mark for the prime number that are greater than 7? No, we cannot, because all we can notice here a pattern that the smallest number we can mark with a prime number is its square. See, 2 square is 4. 2 was able to mark 4. 3 was able to mark 9 as its first multiple, and 5 25, 7 49. And the square of 11 is 121, which is beyond our range, and square of 13 is 169, beyond its range. So we will not check for number that is greater than square root of the given number. So here it is 50. So square root of 50 is 7 point something. So we'll check till 7. So here we can even reduce this loop from running from 2 to n to 2 to root n. And we'll also optimize this loop. We'll start marking from, suppose the loop variable is here I, so it has provided some prime number I, so I am going to start it from I square to n. As we have noticed here, we have seen there here that the first number that a prime number is able to mark is its square. So here I am going to start with I square, so I need not to do unnecessary computations. So after completion of this loop, we can be sure that all the non-primes in the given range, that is 1 to n, are marked, and the numbers which are left unmarked are the prime numbers. So 2 is prime number, 3 is prime number, 5, 7, 11, 13, 17, 19, and 29, 23, 31, 37, 41, 43, 47. These are all the prime numbers that are left unmarked in the array that we have taken. So we can traverse this array and we can print or store all these unmarked numbers as prime numbers. So let us see its implementation. So now let's have a variable n and let's take it as input. So now n will hold a value till which we have to print all the prime numbers starting from 1. Now defining a vector here, vector int v. So this vector v will hold all the prime numbers that it will get from a function primes, and this function primes will take n as input. Now after calling this function primes, our vector v will have all the prime numbers. So now printing them, so auto I colon v cout I space. Now our main function is completed. Now we'll complete function primes. So its return type is going to be of vector int type, its name is primes, and it will take an integer argument. Now as I have discussed earlier, now here I am going to create a bool type array, bool star, let's name it sieve, is equal to new bool, and its size will be n plus 1. Now putting here a for loop. Initially I am going to make all the bool variables as true. So from 0 till n I plus plus, sieve I will be true. Now initially I have considered all the elements as prime number. Now I will make them false. I will mark them as non-prime by making them false. So now putting a for loop here, that it will start from 2, from the smallest prime number, it will go till square root of n I plus plus. So now this loop is going to provide me prime numbers. So inside this I am going to check if that number given by the upper loop is prime or not. So I will check here, see I is true or not. If it is true, then I am going to mark all as multiples. So for doing so, putting here a for loop that will start from I square. And why am I using here I squares? I square I have discussed it earlier. So it will run till j is less than equal to n, and j will increase by I, because I have to mark multiples of I. So I will make it false. So sieve of j is equal to false. So now this number j is marked as non-prime. Now after completion of this for loop at line number 9, we will have array sieve in which all non-primes are marked as false and all primes are marked as true. So now I'm creating a vector which is going to hold all prime numbers. Let's name it answer. Now putting a for loop to traverse the bool array, sieve array of bool type, and now it will run till n I plus plus, and if sieve of I is true means that that bool variable is true corresponding to an index, and that number is a prime number. So I will insert it into our answer vector. So answer dot pushback I. Now I will return answer to the main function. So return answer. Now let's check this code. So I'm providing here input 50. Now let's run it. So yes, it is showing prime numbers from 1 to 50. Now let's try it with other input. Let's say 100. Now let's run it again. Yes, now it is showing all the prime numbers from 1 to 100. So it is working fine. So hope you understood the concept of Sieve's algorithm. Thank you.